so we stay also.
So, the first speaker is Antoine Browaeys from the Institut.
So I guess I'm the first experimentalist. So you won't see too many equations in this thing, but what I'm going to try to explain you is how what kind of studies we've done around using the XY model, dipolar, to study outer equilibrium dynamics in a very specific case. So this will be done with arrays of Rydberg atoms. And the thing is that despite the fact it's open many-body quantum system, we do work hard to make sure that it's actually as not open as possible in our case. So the openness, if you want, is more something we don't want, and that we have because there are imperfections in the system. This is, you will see actually two talks from our groups during the workshop. So there will be a talk today, and there will be a talk of Igor tomorrow. So this is our group at the Institut, and we have a lot of collaboration with theorists actually on every aspect that we study, which is always connected to many-body physics. And so the general theme of what we do in the group is really many-body physics using synthetic quantum systems. So we build our systems atom by atom in a sense. And we try to tune and control the interactions in there and explore many-body physics. So we have three platforms. The first one is arrays of Rydberg atoms that I'm going to talk about. We have this platform where we take an ensemble of atoms, which dense ensemble, applying light. So the light is going to induce dipoles. Those dipoles will interact, and that modifies the way the ensemble scatters light. And so we've got a third experiment using arrays of dysprosium atoms, which kind of combines the tools that we have developed on the arrays of Rydberg atoms together with the physics we're studying there. And so this physics is actually the physics of dissipative spin models. So that falls much more in the central core of the workshop and the subject of the workshop. And Igor will tell you about that tomorrow. So what I'm going to talk to you about today is trying to explore what happens if you take an ensemble of spin 1/2 particles that you pin in space, so they do not move. There is no tunneling, no nothing, no motion, and make sure that they interact through an Hamiltonian, which is this XY model. So it's the usual flip-flop Hamiltonians, it's kind of the extreme, in a sense, Heisenberg model, and which is the XY components. And the thing which is specific to what we're going to study is the fact that the interaction is a 1/r³. And it's not the nearest neighbor interaction, as is usually the case in text. So this is something which is relevant for actually quite a few systems. So of course, if you take magnetic moments in solid states, it is what you have. But also if you have polar molecules, you have magnetic atoms, defects in solid as well, have magnetic interaction, which falls like 1/r³. And so the reason why this 1/r³ is interesting is because in 2D, that's where it will automatically lead to frustration. So the idea is that if you take kind of a square array like this, so the an antiferromagnetic coupling will favor these anti-correlations here along the edge of the square. But so that leads naturally to the fact that you've got positive correlations along the diagonal. And this is in competition, of course, with the natural antiferromagnetic coupling, which would have a tendency, even if weaker, but to destabilize the order that you have here. So we're going to try to see what's the consequence of having this long, so to speak, not long range, but this kind of longer range interaction on the dynamics of the system. And so the way we're going to look at that, so we need a system that implements these XY models. So we're going to look at that using arrays of atoms. So each of the atoms will be trapped in a tweezer. So a tweezer is a laser beam which you focus very tightly on a spot size, typically 1 micrometer. You can place one and only one atom in this tweezer. If you want to have many of these tweezers, you use diffractions. Essentially, your laser beam is diffracted, and each of the spots will be for the atoms. And with that, we can have a various ensemble of atoms. So this is an example of about 200 atoms in a kind of a 1D chain. You can put them in a ring. You can place them in square, in triangle arrays. You can even assemble things in 3 dimensions. And the record today, at least for this platform, is about roughly 800 atoms. So that's what we can get now. All right, so everything I'm going to show you will be done with about 100 atoms. And so now we did interactions, obviously. And so the way we tune the interactions between atoms. So the atoms, you may not have noted that, sorry. The interparticle distance here is a few micrometers. So it means that at such a large distance, there is no natural interactions between the atoms, just too weak. So the way you make them interact is by promoting them to Rydberg states. So Rydberg states are highly excited states of any atoms. We use rubidium in our case. So essentially we use laser to excite them. So let's forget about the plumbing. So it's now a two-level system where you have two Rydberg states of opposite parity. So this Rydberg state, classically, they correspond to the electrons spiraling very far from the nucleus. So it means that the separation between the plus and minus charge is actually large. So you've got large dipole moment. The consequence is that it's kind of easy to drive a microwave transition between this. So this is an example of Rabi oscillations between two states. And you see that, I mean, over a time scale of less than a microsecond, you can rotate the state of the atoms. And from the point of view of the interaction, what is interesting is the possibility of having this kind of exchange interaction where if one atom is in spin up, this is this p state, the other one down, they can virtually exchange photons, and that leads to an exchange interaction. So essentially, if you take one atom in up, then they will coherently exchange their state. So if the system were not open, actually, we would not have the decay. So the fact that we have decay is precisely because it's not an open system. We have coupling between degrees of freedom. And so that implements exactly this sigma plus sigma minus Hamiltonian, which is this XY model, which you can rewrite as an XX plus YY amine. All right, so with this, I will try to show you two experiments that are always out of equilibrium experiments. And I'm not sure when I have started. Do you have the time? Or there is a clock somewhere.
How much? I mean,
you're in 18 minutes.
Okay. So I will try to show you what happens if you place the system out of equilibrium. The consequence of placing it out of equilibrium will lead to first the generation of spin squeezing, we describe, and also the possibility to measure the excitation spectrum of the magnet and see that the 1/r cube does play a role. So this is work that we've done in collaboration with the group of Norm Yao in Harvard and the group of Tommaso Roschilde in New York. They did the theoretical support, so essentially numerics and also some conceptual inputs. So let's start with the generation of spin squeezing. So the basic idea is kind of simple. You just take an array, 10 by 10 array, so about 100 atoms, and you prepare all of them with the spins pointing perpendicular to the plane. And at some point you apply a quench, okay, which is that you place them in the XY plane. So the system is now out of equilibrium and you look at how the system evolves. So the first thing that you can do after this initialization in this kind of so-called coherent spin state is to look at the average magnetization after some time. So essentially, you measure how much polarization you got along, let's say, the y-axis, which is the axis that you've placed, you've initialized the state in. So you have initially a ferromagnet along y, and you just look after some time at how this magnetization evolves. And as you see here, the magnetization kind of decreases, so you depolarize the system. It turns out that actually this depolarization is slower the larger the system, which is a bit counterintuitive, actually. I'll show you why this is the case. So that's the first thing. At the end of the day, this depolarization is not completely surprising. You've got a system with many eigenfrequencies corresponding to the function between the particles. So you kind of dephase the state if this is a consequence of this. But so the question is that can it be more interesting than that? Can it generate some form of entanglement as we usually have when you quench a many-brain system? And the answer is yes. And a weak form of entanglement is given by squeezing. So just as a reminder, so squeezing is a consequence of having a commutation relation between two components of the total spins of the system. So essentially, you start with your coherent spin state. There is the natural quantum noise here associated to the collective spin state, which is a result of the Heisenberg relation. So now if you assume that you've got some kind of interaction, which is a quadratic interaction in the total spin length, so this is an SZ square, which corresponds microscopically to an all-to-all connection. So it's something which is actually hard to implement in a lab. There are situations where you can do that, but that's not a naturally occurring interactions. Then the consequence of that is that this quantum noise will be sheared around this sphere here. And so that's kind of interesting because it leads to squeezing. You can define a squeezing parameter, which essentially is the ratio of the variance along the weak axis divided by the spin length square. And the reason why this is an interesting quantity to look at is because that would be the metrological gain you would have if you were using your ensemble of spin to do a precision measurement. So, I mean, the typical thing that people do are Ramsey interferometry in clocks, for example. And so if you were taking an ensemble of independent atoms, you would have a resolution standard quantum limit. And now if you're using an ensemble of spin squeezed atoms or whatever particles, then you enhance your metrological gain by precisely this. So the more squeezed, the better the resolution. So, and the thing which is important is that at least if you have this one axis twisting model here, which is this SZ square, the squeezing scales favorably with the number of particles. The more particles you have, the more squeezing. So people have implemented that. So there are many experiments that started last century, actually, and have showed impressive results and metrological gain along those lines. But so the point is that, you know, we don't really have, of course, an all-to-all connection. Okay, so we have an interaction with one of our cubes, so it's not strictly speaking nearest neighbor. It's not strictly speaking all-to-all, so it's kind of something in between. So there are two questions now. Is that will it lead to squeezing? That's the first question. And if yes, is this squeezing scalable with the number of particles? And that would be nice because then it can become a resource for metrology. So the answers has been given theoretically first as early as 2014. And so the answer to the two questions is supposed to be yes when you have one over R cube in 2 dimensions. So the reason for this, let's look a bit more in details into this Hamiltonian, and we're going to transform this spin Hamiltonian in a particle Hamiltonian in the following way. So we use the usual Hofstein-Primakov transformation that allows you to rewrite your spin operators in creation and annihilation operators of particles. And if you do all this and you remember, it's very different from the textbook thing, that your spin wave is done on a finite size system. Then what you have is the usual spin wave that you have from spin wave theory after you do Bogoliubov and all this. But you also have an extra term here which comes from the fact that you've got a finite size system. And this operator is kind of interesting because this is something which precisely has a GZ square, a total spin square type of behavior. So it looks exactly like a rotor and an OAT thing. And the second important thing is that this rotor part has a inertia that scales with the number of atoms in the system. So that's the reason why in textbook at the thermodynamic limit, you never have this term because n goes to infinity. But this is something which is a consequence of having a finite size system. The J here that you have, so is essentially the Fourier transform of the potential. Okay, so the nice thing is that now if I forget first the spin wave, I just look at the rotor, which corresponds to essentially the spin wave, if you wish, at Q equals 0. So that's like the collective behavior of the system. I should have an OAT type of dynamics, and therefore it should be scalable with the same scaling as what people have seen for the OAT. All right, so let's do that in the lab. So we do this measurement. So we initialize our atoms in the XY plane, as we did, and after some point, we kind of measure the variance along this around this axis theta here to try to find if there is an angle at which indeed the variance goes below the standard quantum noise. So standard quantum noise corresponds to 1, and indeed we see by doing a measurement along the theta axis that it goes below 1, which is the signature of squeezing. You can also do that for various waiting time, the squeezing kind of building up, and you find out that the squeezing, the variance kind of decreases as a function of time, and then increases again. You have to be careful, this is not enough to claim metrological gain, because at the same time, the system depolarizes, so the length of the amplitude of the signal decreases. So you do need to take the ratio of the variance divided by the length square, and indeed now you've got a squeezing parameter which goes below 1, and that signs the fact that you've got squeezing. So now the next question is the squeezing scalable? And so I just come back to this depolarization curve that I showed you. So essentially here, the more atom you have, the slower the depolarization. And the reason for that is precisely coming from this momentum of inertia, which actually increases with the number of particles. So the more particles you have, the slower the dynamics, which is a bit counterintuitive. And say it would decohere or whatever, but actually that's not what happens. And you also can measure the time at which the squeezing occurs, and the more atoms you have, the longer it takes for it to squeeze. And at the end of the day, we can measure the squeezing parameter as a function of the number of atoms. So there are many information on this, but essentially, for the number of atoms we explore, which admittedly is actually pretty small, it's up to 100, we do find that the squeezing increases or improves, if you wish, as up to about 100 atoms.
Do you do it at the optimal time?
We always have to kind of readjust the optimal time.
Okay.
Yeah, to make sure that
It's the best you can do this.
Yes. Yeah. The squeezing we have is certainly not a world record. So -5 dB is not extremely impressive. If you compare to -20 dB that people should have with the OAT.
So in your picture, the spin waves affirm momentum are just a noise that are damaging the squeezing of the collective moment.
Yes. So, sorry, what's the beginning of the question?
Yes. So the spin waves affirm momentum. In
Yes.
your picture, are just a noise that is damaging the squeezing of the collective spin.
That's exactly that. And actually, what you see here, this kind of bump, you see before it branches onto this kind of scaling, is precisely the influence of the spin wave. But I will come back to the spin wave in a minute. Right. So the conclusion of this is that at least we could check that indeed the squeezing is scalable with atoms. It's not a lot, but it's fine. And we have that with other type of system that shows that it's not only OAT which can produce squeezing, but you can have a longer range interaction that does produce squeezing. Okay, so now, last, I would like to show you the connection with the second part of this out of equilibrium dynamics. We had the collective behavior, so now let's look more closely at the spectrum of the excitations. So this is again this rotor spin wave theory. So we've looked at this thing here, but now let's look at the finite momentum part of the Hamiltonian. So once again, this spin wave part now has a frequency which is related to the Fourier transform of the potential. And the thing is that this is not exactly the same because of the staggered coupling, if you have ferromagnetic or antiferromagnetic coupling. And the prediction for Q goes to 0 is the following. If you have either ferro or antiferro coupling and nearest neighbor interaction, then you should have a dispersion relation which scales linearly with Q, the momentum of the spin wave. Things are different if you have dipolar interaction. If you have a dipolar interaction, the antiferro is unchanged, while the ferro goes from Q to square root of Q. So those were things that people realized about 10 years ago. So it's not a textbook material, it's something which people realized not so long ago, when this is actually old findings. So the 1/RQ does modify the dispersion relation. And so just one very, very hand-wavy way to understand why it's not modified for the antiferro is the fact that precisely you've got the frustration. So the frustration has a tendency to destabilize a given order, making the interaction effectively short range. So that's the reason why, even in the dipolar case, with the frustration, you kind of recover the nearest neighbor type of behavior. Yep. Sure. It is geometry dependent. The frustration is much larger in 2D than it is in 1D with an 1/RQ, because here the destabilization is 1/8, while in 2D it's 1/2√2. So I fully agree with you. Okay. So the way that people usually probe the excitation spectrum of the system is you prepare the ground state of the system and you perform some kind of excitation that you probe. The problem is that for us, although we've done it, but preparing the ground state of the system takes a lot of time and a lot of coherence time. So here we have another way to do this kind of thing. It's to measure the dynamics following the quench that I mentioned, the exact same quench as we were using for the squeezing. And we having in mind the following idea. This kind of quench protocol, where you prepare your state in a mean field approximation of the true ground state, differs from the true ground state by precisely the spin wave. So the preparation of a mean field separable state is precisely injecting spin waves in your system. Okay, so that's the reason why you can look at the dynamics of the system. It will be a signature of the spin wave you have injected in the system. So once again, you start from either the ferro or antiferromagnetic mean field ground state. So it's an easy to prepare product state. So it's not a true ground state, but precisely the difference is the fact that you have injected spin waves in the system. It can be put a bit on a firmer ground. I mean, that was pointed out by Tommaso Rosilde and Laurent Sanchez-Panonza, that if you introduce now the time-dependent structure factor, so it's not exactly what people have in mind in condensed matter physics, and this is here exactly the same time Fourier transform, the spatial Fourier transform of the correlations at a given time. There is no out of order time. You Fourier transform the thing, and at least in the linear spin wave theory, you find that this guy oscillates at twice the frequency that you want to measure, which is the dispersion relation. So, I mean, the reason why there is a factor Q2 is because actually it's a Q minus Q preparation of spin waves that you have. Okay, so let's do that. So we start again for our 10 by 10 array. We perform the exact same experiment as the one I discussed for the squeezing. So you just prepare them along Z, quench in the XY plane, and you measure after some time the correlations in the system. So it becomes a 2D map. So that's essentially plotting the sigma I, sigma Z connected correlations that you have. And you see as a function of time how the correlation evolves in this 2D map. So there is I and G because it's a 2D system. So you make this 2D system actually a 1D system just by averaging for all the spins that are at a given distance from origin here. And you plot this space-time diagram of the correlation as a function of time and as a function of distance. So, and you see that there's some kind of structure. You see that for nearest neighbor, very rapidly you build anti-correlations. Anti-correlations means blue, while you have this kind of plume of positive correlation. So the dynamics is actually reasonably complicated. You can Fourier transform at every time. So essentially you Fourier transform in space, and so along this line. And you can measure as a function of time these time-dependent structure factor from which you can extract the spin wave. We can discuss in details how we extract the spin wave frequency. Yeah.
Will it make much difference if we use the metropolis distance rather than the?
We've tried that. No, it doesn't make too much difference, at least for this data. Okay. Yeah. And so from this, you can extract the frequency. There are some subtleties that we can discuss if you wish. So the dots here with the arrow bars are the data. And all the other square circles corresponds to various theories with finite size systems. Yeah.
In the spin wave, you get this simple time dependent as cosine, but there, I guess, the curves are different. So what are the curves?
Yeah. So why? I mean, of course, it's not a sign. And why is that? Because it's a finite size system. So the finite size system means that essentially your spin wave bounce on the edge and produce some kind of steady. But this is a real difficulty to do the analysis on this finite size system. But I mean, that's the largest we could explore. But indeed, the analysis of this data, we had to spend a lot of time to connect that to the spin. You can do the analysis actually in two different ways. Either you look at the frequency, which is what we have here, or you look at the steady state value around which the oscillation takes place. And actually, it's a much more reliable data, because here it fits exactly what we expect from the theory. Theory being done again on a finite size system. And so the last thing is that we do the very same experiment now for the antiferromagnetic case. So I should say that here you see that it's kind of suggestive of this quote of Q behavior. Of course, it's a finite size system, it's not exactly quote of Q. So now if you want to do the very same thing for the antiferromagnetic case, how do you do that? The problem is that in our case, the coupling is naturally ferromagnetic. Okay, so how can we explore the antiferro? Just by applying a different trick. Instead of starting from the ferromagnet along Z, we're going to prepare the staggered configuration along Z, so an antiferromagnet. And we apply the very same quench protocol. So the reason why this is interesting is because now the antiferromagnetic configuration for ferromagnetic coupling is the highest excited state of the Hamiltonian, which is to say the ground state of minus the Hamiltonian. But as you know, the dynamics doesn't depend whether it's a plus or minus. So you just using this trick, we have access to the second thing. So we repeat the very same experiment. We have something which hardly oscillates. We're going to discuss that in a minute, but from which we can again, using kind of subtle analysis, extract the dispersion relation as well, which now seems to be linear. So there are two remarks. Why don't we see some oscillation here? So it's kind of interesting because it turns out that the mean field antiferro that we prepare is a poor approximation of the true ground state, while for the ferro, it's a good approximation. So the difference is that in this antiferromagnetic case, we excite many more spin waves. So now the spin waves can interact, and you go beyond the linear spin wave theory. You need to take into account the interactions between the spin wave, leads to this kind of Magnon decay. So I'm not necessarily going to claim too much about this because unfortunately the time scale is the same as the one over which the system naturally decoheres, so it's an open system. So, but at least it's suggestive of this. And so now we see that indeed there is a difference between the ferro and the antiferro case, which is kind of an experimental picture of the fact that this 1 over r cube plus frustration modifies the way the system behaves. And that's essentially all I wanted to tell you. I already mentioned that through the questions, but it's kind of annoying. We only have a 110 by 10 array. So it means that where we would really like to have points around q equals 0, we don't have enough because the system is not large enough. We need to work towards larger systems. Okay, so let me just conclude and thank you very much for your attention.
So maybe I want to come back to my question. Do you have any perspective for squeezing a finite momentum? So in all these systems that are not OAT, you could also define a squeezing parameter for a given wave vector at finite momentum. There is a definition of that. Just for you to respond.
So it's a good point. So I'm not sure. Okay, we kind of discussed that. We have not done a careful analysis, but indeed, at a given Q, some analysis of the data seems to indicate that we also have squeezing. So it'd be interesting to discuss that more. We haven't pushed this, but that's something we discussed here.
Is it an interesting platform to study transport? Of course, for example, particle charge or energy.
Yes, and that's actually what we're doing. I mean, at the moment, for example, we're kind of going beyond the spin 1/2 model, implementing some kind of TGA model where you place some excitation in the loop. But in a sense, this is already a transport experiment. It's kind of flip-flops if you place excitation and you loop.
When it was for the long term, so what is ultimately the largest system size you can imagine?
The thing which is realistic within, let's say, a few years, I'm not saying that it's already the case. I showed you a platform with 1,000 atoms nearly. So the community is getting there. The problem is now to keep the control also on each of the manipulation for large system scale. But 1,000 seems to be a realistic goal. Now, if you're asking me a few million, well,
it's more of a control than the laser power to trap all
the problem is that beyond a few thousand, we have a problem just of laser power available to crack the atoms. You know, for a very long time, I thought that a few hundred would be enough. And that's the first experiment we're doing, where actually we would like to have a much larger system size to access really the Q equals 0 region. So.
What about dissipation? Have you mentioned it?
Point in that direction.
What about dissipation? So you mentioned at the beginning, but then I kind of lost it.
Okay. There are two kind of dissipations in this system. The first, which is not dissipation, is the fact that on each realization of the experiment, we do not prepare exactly the same initial state. When I tell you, you prepare the ferromagnet, it's a ferromagnet with a few spin flips. So essentially, we would rather say that there is entropy in the initial state. It's not a zero entropy state. Okay, so that's the first thing. So it's more an imperfection, and that we translate into the dynamics as some kind of the spin exchange that I showed you with some damping results from something a bit more subtle. Ultimately, there are many sources here, but the ultimate source is the fact that we've got a finite size extension of the spatial wave function of the atoms. They are not infinitely pinned in the tweezer. So there is a kind of, the 0-point motion thing. And the interaction energy is 1 over r cube spin operator. So it couples internal and external degrees of freedom. So in a sense, this coupling to motion acts as an effective decoherence in the system, if you only look at the spin degrees of freedom.
And because you showed that the data with the theory, so the theory was done with...
Yes. And this theory, which I showed you, and it is kind of flip-flop. You're saying the theory, which theory?
No, in the lots of
where the signal was decreasing. There was
Yes.
some theory.
Yeah, and so the model is done by having put, it's just two atoms. So for this one, it's easy to do the theory, where we have included the external degrees of freedom that we have independently measured. We kind of know what is the spread of the wave function. And this is a fundamental problem because it means that despite the fact that you are as cold as you can be in your tweezer, we are nearly in the ground state of the tweezer, you still have this coupling which shows up. And all platforms will have this problem. Ions have kind of this, all have this. So.
Is it possible to do a cross-check experiment where you make the atoms farther away so that the dipolar coupling, the frustrating dipolar coupling is less important, and you can recover the spin waves of the standard ferromagnet?
The problem is that in this case, I don't have any coupling at all.
So if you lose one, you lose also the other one.
Yes.
Okay, because it's just a geometric factor.
No, you're saying, can I go to 1D, for example?
Going in regimes where you could probe.
Wait, very good point. So what we've done, I haven't showed the results here, we are writing them up. We do the very same experiment in 1D.
Okay.
And in 1D, you don't have this modification of the dispersion relation. And we do recover a linear dispersion relation. So really this kind of bending of the dispersion relation is a consequence of having one of our cube. So that's the only way we could do the counter experiment. Now we're thinking about changing the range of the interaction. It's using two Rydberg states of the same parity. We can have a 1/6 interaction flip-flop. And the point is that it's not exactly the XY, it becomes an XXZ model. So things are not exactly the same. And then we also recover a linear dispersion relation.
Okay. Thank you.
So we should move on. Let's play.